Hey everyone, and welcome. Today we're doing something really cool. We're going to peel back all those layers of abstraction and build a UART driver completely from scratch on an STM32 microcontroller. We're talking direct, register-level programming. Let's dive right in. So if you've ever worked with STM32, you've probably called a function like hail UART transmit, right? You just pass it some data and poof, it magically appears on your serial terminal. But have you ever stopped to wonder what's really going on under the hood? What bits are being flipped in which registers to make that all happen? Well, that's exactly what we're going to uncover today. Here's the game plan. First, we'll talk about why you'd even want to go bare metal. Then, we'll lay the essential groundwork with clocks and GPIOs. After that, we'll configure the USRT core itself, build our simple transmit and receive loop, and finally, we'll wrap up with some common pitfalls and where to go from here. Okay, so why bother messing with registers when we have perfectly good libraries like HAL? Honestly, it boils down to three big things: having ultimate control, squeezing out every last drop of efficiency, and gaining a real, deep understanding of how the hardware actually works. Look, it's all about a fundamental trade-off. The HAL and LL drivers, they're fantastic for getting a prototype up and running fast. They're super convenient, but that convenience comes with a price, usually some performance overhead, and it kind of hides what's really going on. When you go bare metal, you're taking off the training wheels. You get total control over the hardware, which means you can write the most efficient, optimized code possible. And maybe more importantly, you stop being just a user of a library and you start becoming a master of the silicon itself. All right, let's get our hands dirty. Before any peripheral, like our USART, can do a single thing, it needs two fundamental things. First, it needs a clock signal to power its internal logic, and second, it needs a physical connection to the outside world, and that happens through the GPIO pins. The first rule of Embedded Club is pretty simple. No clock, no talk. If you don't give a peripheral a clock, it's basically a dead piece of silicon. Forgetting this step is probably the #1 source of bugs, where you spend hours debugging something that was never even turned on. That's why it's always the first thing we check. And this isn't random. There's a strict hierarchy here, all managed by the Reset and Clock Control Unit, or RCC. First up, you have to power the entire GPIO port where your TX and RX pins live. Second, you enable the alternate function clock. This is what lets you hand those pins over to the USART. And then finally, you enable the clock for the USART peripheral itself. You miss any one of these, and your code is just going to fail silently, leaving you scratching your head. So what exactly is this alternate function mode? Well, think of it like a switch on a railway track. By default, a pin is just a general-purpose input/output. But when you flip it into alternate function mode, you're basically rerouting the track. You disconnect the pin from the normal GPIO logic and connect it directly to the internal hardware of a peripheral. In our case, the USART's transmitter and receiver. And here's the exact setup we need. The transmit pin, or TX, has to be set as an alternate function push-pull output. Push-pull just means the pin can actively drive the line high and low to send our signals. The receive pin, RX, is set up as a floating input. It's just sitting there, listening for voltage changes, without pulling the line in either direction. Okay, our physical connections are all set up. Now, we can move on to configuring the brain of the operation, the USRT peripheral itself. This is where we set the rules of the road. The speed, the data format, all the rules of communication. The first and probably most critical setting is the baud rate, how fast we're talking. On these STM32s, the hardware uses what's called a fractional baud rate generator. And see that 16 in the formula? That's a 16 times oversampling rate. It's actually a key feature for making communication really robust, because it samples each incoming bit multiple times, which helps it deal with small clock differences between devices. Let's just walk through a real example so it makes sense. Say we want a common baud rate like 115,200, and our system clock is 72 megahertz. We just plug those into the formula, and we get a divisor of 39.0625. Now the hardware register splits this number into two parts. The integer part, 39, is called the mantissa. For the fractional part, that 0.0625, we multiply it by 16, which gives us 1. We then just mash these together into the register. The mantissa, 39, goes in the upper bits, and the fraction, 1, goes in the lower bits, giving us our final register value of hex 271. Next up is the main control register, CR1. There are 4 bits here that we really care about. The M bit sets our word length, usually 8 data bits. TE and RE enable the transmitter and receiver circuits, and UE, well, that's the big one. It's the master switch that brings the whole peripheral to life. And the order you do this in is absolutely crucial. Set your word length first. Then enable the transmitter and receiver. And only then, as the very last step, do you set that USART enable bit to turn it all on. With all that configuration out of the way, we are finally ready for the main event, actually sending and receiving data. We're going to start with the simplest possible method, which is called blocking or pulling. Basically, our CPU is just going to sit there and wait for the hardware to be ready. So, how does our software know when it's safe to send the next byte? It keeps an eye on the TXE flag. TXE stands for Transmit Data Register Empty. When the hardware sets this flag, it's pretty much raising its hand and saying, "Hey, I'm ready for the next piece of data you've got for me." And this one single line of code is the heart and soul of our blocking transmit function. It's a while loop that literally does nothing but check the status register over and over and over until that TXE flag gets set. We call this a busy wait because the CPU is busy, doing nothing but waiting. As soon as TXE is set, the loop breaks, and we can safely write our next byte to the data register. Now, this is a super common gotcha, so listen up. The status register actually has two transmit flags, TXE and TC. TXE tells you the buffer is empty, so you can load the next byte. This is what you use when you're streaming a bunch of data. But TC, transmission complete, is different. It tells you that the very last bit has physically left the wire. And here's why that matters. If you check TXE before shutting down your device, you might actually cut off the last byte of your message before it's fully sent. You only wait for TC when you have to be absolutely sure the entire message is out the door. Okay, so on the receiving end, the logic is pretty much the same idea. We have a flag called RXNE, which means Receive Data Register Not Empty. The hardware will set this flag for us the instant a complete byte has arrived and is just sitting in the buffer, waiting for our software to come and pick it up. The process here is just beautifully simple. We do another one of those busy wait loops, but this time we're waiting for the RXNE flag to pop up. Once it does, we just read the value from the USART's data register. And here's my favorite part. The moment you read that register, the hardware automatically clears the RXNE flag for you, getting it ready for the next byte. No manual cleanup required. We've covered a ton of ground, and just like with any low-level programming, there are a few classic traps you can fall into. So let's go over them real quick, so you can hopefully avoid hours of frustrating debugging. I've seen these trip up even experienced developers. Number one, by far, is forgetting one of those 3 clocks. Number 2, a simple math error in your baud rate calculation that just leads to complete gibberish on the screen. 3, misconfiguring the GPIO pins, especially forgetting to set them to alternate function. 4, an overrun error. This happens if a new byte arrives before you've had a chance to read the old one. And finally, like we just talked about, confusing TC and TXE and when to use each. So there we have it. We've built a simple, reliable, polling-based UART driver. And it works. But that busy wait loop, where our CPU is just spinning its wheels, is incredibly inefficient. It's wasting millions of clock cycles that could be doing something useful. And that brings us to a final question. What if we could flip this whole model on its head? Instead of us constantly asking the hardware, "Hey, is it there yet? Is it there yet?" What if the hardware could just tap us on the shoulder and say, "Excuse me, I have something for you." And that, my friends, is the perfect lead-in for our next topic, interrupts. Thanks for tuning in.
If you like this one, the YouTube algorithm says you're gonna love my other videos, so go check them out.